that said, I will minimize my video and trust the way this is working, and I think get started. And so we're talking about flying triangles, so I guess that means we should probably have some triangles. So let's start with a triangle which has, I'll get my presentation stuff going on here. An angle of 1/2 of a straight angle, 1/3 of a straight angle, and 1/6 of a straight angle. I'm using it in terms of fractions of a line instead of in terms of degrees, because that's now a little bit more natural. And one of the things you can do is you could reflect this triangle along an edge, like along the short edge, or along the long edge, or along both. And you can keep going reflecting it. And immediately this is going to bring you to some nice warm-up questions. And so some of these warm-up questions are, here we've got angles. Think about what other angles you could put in the triangle to come up with interesting tilings and tilings by reflection. And this is not exactly a well-posed math question. It's a nice math circle question because you can make math out of it. I'm not saying specific rules about this, and so by changing the rules, you can get different features and different things. Another question that I'll have you think about in our first intermission after the warm-up is that if you reflect in one line and then in a second line, and those lines make an angle of 1/2 a straight angle, what's the resulting combined motion? So what happens if you do 2 reflections? What happens if the lines meet in a different angle, like in a 1/3 of a straight angle? What's the combined motion of doing a 1/3 rotation? So I hope you understand what the questions are. And so if you don't understand what I'm asking about these, by all means, make sure you interrupt and say, dude, you're not being clear. Okay? So if we continue this process, what's going to happen is we're going to fill up all of space. Well, I haven't filled up all of space here, but I filled up a bigger chunk of space. We can imagine that we keep going and we get this pretty tiling of the plane. Looking at this, I recognize we're going to have a spoiler alert for maybe, maybe not. There's a couple of ways we could move through space. And so here we've put the spaceship from the Guardians of the Galaxy into our space. I might call this space 2-3-6 space because it's based on a 1/2 angle, a 1/3 angle, and a 1/6 angle. And there's a couple of motions we've got. One obvious motion we could do is we could rotate this ship through a 1/2 angle rotation centered at that point. And if we do it, kind of does that. So it moves from one pair of triangles to another pair of triangles. It just fits perfectly. Another motion we could do, which, the first one I called R2 for the twofold rotation. This I'm calling R3. In fact, a good way to do mathematics, it's bad for relationships, bad for date nights, but awesome for math, is to guess what's going to happen next. You should be able to guess what R3 is before it happens. Don't guess on a date because you want the person to hear what you're going to say and you want to listen to them. But in math, if you guess and what happens is what you imagined it would, then you're understanding it. Make sense? So now we have some interesting players. We've got the Guardians in their spaceship, and we have the universe here. And so we can think about some warm-up questions, some first warm-up questions. We'll also have some second warm-up questions. So this is what I might call generation. What sort of motion can you generate? Can they get to everywhere they want to be in space? So a really natural thing. So I'm going to change the notation a little bit, and I'm going to let R stand for the 1/3 rotation, or the R3 rotation, and I'll let S stand for the R2, or the 1/2 rotation, so that we don't have more cumbersome strings of letters. And I want you to think, is it possible for the Guardians to visit any pair of triangles meeting along a short edge like that, using a combination of those things? If the answer is yes, why? If the answer is no, which ones can't they reach? I'm also interested in combinations of moves that make the trip go in a round trip, so it goes in a loop. And what can you say about those? This is some pretty pictures to play with, which are always good things. But I can make something look a little bit different. It's going to take something that many of you will have seen, but some of you may have not.
So just there is a question, and I want to go back to the previous slide if you can, just to clarify.
Absolutely.
So S is this is from Kabir, and he says S is a 180 degree. He just wants to clarify. S is a 100, what we would call, I mean, I know you have the name half revolution, but it's a 180 degree turn, and I'm guessing it's about the midpoint of the long leg of the triangle. That's the center of rotation.
S is, as you say, 180 degree or pi rotation, or 1/2 rotation. So pi radians, 180 degrees, 1/2 rotation.
And similarly, the other one, R, is a 2 pi over 3 or 120 degree, and it's a rotation about the vertex that you just highlighted. But again, as the ship moves, it'll be whatever vertex that point is at.
Right. And now, when you're exploring mathematics, doing things on your own makes sense, making up your own things. Partly you want to look at problems that you haven't seen before. Though if there is an existing literature and existing conventions, it's good to follow the existing conventions so that when you read other things, it'll be easier. And so in particular, when I'm doing these rotations, I will consider counterclockwise rotation as the positive and standard rotation, because that's what we do in most math classes. Thank you for the questions. Somewhere here, I imagine there's a chat, but I think it's working a lot better to.
Okay, so I'm going to pass another question that John asked is, so if the edges temporarily hang outside the space, I mean, you've only drawn the space up to a certain, there's a boundary beyond which is the rest of the slide. And I think he's clarifying that in principle, it's okay if you go outside that boundary, at least while you're doing the rotation.
Right. So the intent of this picture is that this picture continues infinitely. And so every time I have a triangle, I am reflecting it across all edges and all way, this thing is extended all the way out infinitely far. And so, of course, I can't draw infinitely far. My patience ran out after however many triangles are on this slide, but I think it's enough to give you a pretty good sense of what it would be. So yes, thank you. And so I'll go back, because we're going to have a similar question without the geometry based on matrices. And so here on this top line, I'm describing matrix multiplication by an example. Basically, you take a column, you turn it sideways, and you multiply and add. Hence 1 times x plus 2 times y and 3 times z. and 4. And so, once you see this pattern, you can generalize it to any two suitable boxes of numbers where you have the same number of columns on the one on the left as you have rows on the right, so that they line up. It's a little uncomfortable as a math educator to just tell you a formula and tell you to compute this way because I said so. There's a fair bit of logic and meaning to why we multiply matrices in this way that I'm not going to go into. Maybe even worse here is we have this combination for a 2 by 2 matrix called the determinant, which is A times D minus B times C. It's this expression here. This one I can't continent not at least giving you a reference to where you can see it. This is one of the things on the web page where I said I'm putting materials for this class. You don't have to see it now, but in the intermission, you might choose to look at this. We will find a way of yelling at you when we come back from the intermission. Certainly maybe after the talk, if you've never seen what a determinant means. This is often taught by educators just telling you the formula. And in fact, you should turn it around just backwards and start with the meaning and compute it and figure out that this is the right formula for the right thing. In fact, it's a certain area. Once we have these concepts, I can define a collection of matrices. So this is going to be the 2 by 2 boxes of numbers where each number is an integer. Oh no, that's a major typo. I will change that. That is supposed to be a 1. Let me make that bigger. That's kind of embarrassing because this is one of the major players in our group. So once we have that, seems like, is there another question?
Yes, there's a question about the Blackboard bolded Z. I think it has shown up in the math circle before, but I also think it's not a bad idea to define it.
Awesome. Yeah, don't let me. So when I write something in Blackboard bold, that generally will be a set of a collection of numbers. And I'm not going to write them all down. This is 0. It's a plus and minus 1. It's a plus and minus 2, ... It's all integers, both positive and negative, so all numbers with no fractional parts. It's all rational. Whole numbers plus and minus sign, plus and minus 3, 7, 1, 8, 6, like that. And so with that said, let me tell you some interesting elements here. There's this matrix R, this matrix S, and this matrix T. And there's some analogous questions like, can you get any 2 by 2 matrix expressed as a product of S's and T's? Which you should think about it on your own. Something that's related, there's a hint, which this is also posted on the warm-up page. And then a challenge is to show how you could express R and T inverse just as products of S's and T's. And find some loops, some relations between S's and T's. And so I think I've got maybe 6 questions for you to think about, and I think it's probably ready to do an intermission. There's see if you can figure out how to generate a general ABCD matrix using just products of S's and T's. See if you can get this matrix in particular using a product of S's and T's. See if you can get T inverse. T inverse is going to be the thing such that if I do T inverse times T, I would get a matrix that looked like 1, 0, 0, 1. The reason that's useful is if I take a matrix like 4, 2, negative 1, 5, and if I multiply that by 1, 0, 0, 1, in this matrix multiplication land where we're turning this sideways, if I put the 1, 0 up here, I'd multiply 1 times 4 is 4, 0 times negative 1. So I'd get a 4. And then I'd get a 2, 0 times 5. And then if I do the same thing, turning the 0, 1 up on its head, we'd get 0 times 4, negative 1 times 1. So negative 1. 0 times 2, 1 times 5, 5. So you see that this particular matrix kind of acts like 1 acts in numbers. Multiplying a matrix by it doesn't change the matrix. This is called the 1 in the land of matrices. And so the inverse of t is going to be a matrix that you'd multiply by t to get this. So you see Brandon's joining. It's probably a good time to summarize the warm-up questions and show you the places where they are. So there's these 3 questions that we see here. There are also, from the very beginning, these 3 questions about what angles can you make in triangles? What happens if you do a reflection and then another reflection about 2 lines that meet at an angle, which the angle's a half of a straight angle or a third of a straight angle? And those are our questions. With that, I will bounce to our intermission